My name is Sietse de Vries. I'm a PhD student at the Building Lighting Group at the Eindhoven University of Technology. And my supervision team consists of Dr. Juliette van Duinhoven, Professor John Medeljevic, and Professor Heliante Kort. And so the title for my presentation of today is Can Body Worn Dosimeters Serve as Reliable Proxies for Measuring Eye-level light exposure? So what I will do is first give some background. So basically explain a bit how did we get to this question. Then I will go over the literature related to this. Then I will show some things from some of the experiments we did. And then I'll present some takeaways, basically based on everything I will show today, like what are the main key messages and what's the outlook for the next steps. So before I start, I should give a small disclaimer. So this is all work I've been working on mostly for the last year as part of my PhD. So it's all fairly recent work, and it's we will present it over 2 manuscripts, but it's still currently in peer review. So it's not yet peer reviewed. And to start with some background. So we as humans, probably everyone knows, we experience quite some different environments during our day. And in each environment, there's quite some different lighting. So typically, the lighting we experience during a full day we refer to as personal light exposure, or the light received by the eyes over time. And as you probably know, as we've seen in research and also just from your own observations, this lighting is quite variable in terms of intensity, in terms of spectrum. So for example, daylight is quite a different spectrum than most electrical lighting. And as well, there is variability in terms of the directionality of the lighting. So we have environments that have relatively uniform lighting coming from all directions, but also, especially indoors, quite some directional light sources. And personal light exposure, why are we interested in this? Well, we've seen that for real world data, there are quite some interesting use cases. So as you know, probably for non-image forming effect studies, so for example, studies on the impacts of lighting on human sleep or alertness, if we do those in laboratories, then we typically know quite well the exact amount a person was exposed to. On the other end, in the field, of course, there are many factors that have an influence. But if you want to do a field study on non-image forming effects, then besides recording, for example, alertness or sleep patterns, you also need to know how much lighting a person was exposed to. So if we have quantifications of the amount of light a person was exposed to during a day, we can use those in field studies on non-image forming effects. And similarly, if we know for a large group of people the light they were exposed to during a day, we can also use that for studies on myopia development. So basically, to get this data, there are multiple methods, and we refer to them as quantification methods. So the first one, most commonly or quite commonly used, is light dosimetry, which basically involves wearing a small sensor on the body. We also have lighting simulations, surveys, and also we can use location-bound measurements to get an estimation of the light the person is exposed to in a certain space. Today, we'll only be focusing on light dosimetry. And light dosimetry, so basically is the continuously measuring a person's light exposure using a small wearable light sensor. Nowadays, there are quite some terms for such sensors, so you also see them being referred to as light loggers, light dosimeters, or just dosimeter. I will use just dosimeter today, but basically they are all different names and they have different origins, but they're now mainly referring to the same types of devices. So in recent years, there are quite some different devices available. So a review of that was published this year by Van Duinhoven et al. So they reviewed 53 different devices that were currently available or recently available. And we've seen these devices, so they come in a lot of different types of shapes, different form factors. And they also worn at different positions on the body. So just to give some examples, for example, we see devices that can be worn as a wrist, as a watch on the wrist. We see devices that are specifically designed to be worn on the clothing or around the neck, so mainly worn on the chest. And also we see devices that are designed to be worn on a pair of glasses. So these are just some examples. There are many different types out there. And when you use such a device to do research in terms of the performance of such a dosimeter, they actually two different types of questions you can ask before you use these to do measurements. So the first one is, if I use my device, does it actually measure the lighting correctly? And that mainly refers to the intrinsic performance of the sensor. So if you have your device, you put a certain light source on it in the throat conditions, then you can check if it can actually measure the lighting correctly. So this is more about the calibration of the device. On the other hand, you use the device to measure a certain quantity, so in this case, a personal light exposure. And then you can also ask yourself, does the dosimeter measure the right light? So basically what this is about is the in situ performance, and it's whether the device captures the intended illumination. So typically, or basically what we mean with this is if I would use a chest-worn dosimeter, so it's placed on my chest to measure my personal light exposure, then the device actually measures over there. Well, typically, for terms of personal light exposure, if we define it as the light exposure at the eye level, then we would like to know the lighting over there. And in both of these performance factors, I will go a bit more in depth. So in terms of the intrinsic sensor performance, so basically this relates to laboratory calibrations. And to do this, there are different standards and guidelines available. So we have some reports from the CIE, basically describing the performance of photometers. So this is also for laboratory devices. And we also have more recent reports for spectral calibrations. And there are many different indices described to do these calibrations for a lot of different sensor aspects. Just to give some examples, for example, the directional response index. So if you have a device that can position a light beam at different angles on the dosimeter, so the dosimeter is now here on this table, then you can check how well does the dosimeter respond to light coming from different angles. Another index is the linearity index. So if you have an Ulbricht-sphere, you can check if I put different type of light levels on the device, how well can it measure all these different levels. And yeah, so the main takeaway here is basically we know dosimeters, so especially the older devices, so from around the 2010s, that generally some had relatively bad performance, so that they were not so accurate in terms of their intrinsic performance. But we've seen in more recent years that actually the quality of these sensors has been increasing by a lot. So it's in most cases not comparable to laboratory grade photometers, but it's more and more getting there. And also we have some or quite some methods available to characterize this uncertainty. So we know there is some uncertainty in your data because the device sensor may not be accurate enough for all kinds of purposes, but at least we can quantify this uncertainty. Then regarding the in situ performance, there are a bit more questions over there. So 2 slides ago, I said we want to know if we're measuring the right light. And then first, of course, we should ask ourselves, what is actually the right light in this case? So if you would do a study on non-image forming effects, then typically we're interested, or most optimally, we would like to know what is happening on the retina. So how much lighting does your retina receive? Or maybe one step back, actually, how much lighting do we get on the cornea? And I guess the good first thing to realize, even though we would like to know what's happening on the retina, if you would place a dosimeter as close to the eye as possible, so more or less the optimal position, then it would always measure a bit in front of it. And also, most importantly, it would measure light coming from a hemisphere. So all dosimeters that use standardized units, so for example, luminance, irradiance, or any spectral characterization, they will always measure light incoming from a hemisphere, since that's just the definition of luminance. So typically what can happen then, if you're, for example, indoor in an office space and you have lighting overhead, then the eye will actually be a bit shaded by the facial geometry, but your dosimeter with a hemispherical view will actually measure incoming light from the ceiling. So that's the first thing that can cause differences between what you would like to measure and what you're actually measuring. And it's actually quite an interesting topic. But today we're actually not going to focus on this field of view occlusion of the human eye. So that's basically what we use to refer to the shading by the facial structure. But instead, we're going to look into if we take this eye level dosimeter as the ground truth, what would then be the differences if we look into body-worn devices? And well, of course, to investigate what are the differences between light exposure measured at the chest, for example, at the wrist, relative to eye level, we first looked into literature. So I will present some of the literature reviewed for this. And actually, before we really go into these differences, maybe you're now asking yourself the question, so why wouldn't we just measure at the eye? Since that's relatively straightforward, would be the best position to measure any eye level light exposure. So also described in various recent papers, we could say there is a bit of a trade-off in terms for measuring at the eye. So on the one hand, you want your participants to be comfortable while they are wearing this dosimeter, since especially in field studies, we're trying typically that participants just do their normal behavior, live their normal day, and then we record the lighting and some other factors. So if they're not comfortable with the device because it's a bit obtrusive, if it's too big, then they may not wear it continuously, so you get non-wear and lower data quality, or they may alter their behavior. Same with how they experience it. So if it's like in terms of visual experience, they don't like it or they don't feel comfortable to wear it in a social setting, you also get changes in behavior or, for example, non-wear periods. So on the one hand, they should feel comfortable. And of course, in terms of validity for capturing actually eye level or personal light exposure, we would like to measure as close to the eye as possible. Well, regarding the practicality, so typically in older light dosimetry field studies, we saw in the discussion that there is some note on the devices used. So if people had problems with them, if they didn't like it, or if there were positive experience. And actually more recently, we have some studies that specifically investigated the attractiveness and the acceptability of dosimeters, dependent on the position on the body, but also on the shape of the device. And well, we now have some studies. We still see we actually have a need for additional studies using real-world design and context to investigate this. But generally, we see that people prefer a device on the chest or on the wrist, or basically on the body, more than a device close to the eyes. And so basically, this makes the case for us. Okay, if we know, probably we need also to have devices to be worn on the body, especially if you want to measure for long term, then people just should feel comfortable with it. So that's why we're basically came to this question, like, okay, if you would measure away from the eyes, what is then the difference, and mainly the uncertainty of your measurement data. So when looking into literature, basically for studies that compared measurement at multiple locations on the body, we actually found 13 studies. So basically these studies, some really had a specific research question, basically comparing the differences between light measurements at multiple positions on the body. Some were more on the development of a new dosimeter type, and then they also did some measurements of different positions to get some illustrative data on what are the sizes of possible differences. And if we look a bit into these papers, so the first one is already from 1983, then there was one in 1990, one in 2001, 3 more in the 2010s, and just in the last 5 years, there were actually 7 more. So if you all combine these, then, well, the first thing you immediately notice is that there are actually quite some competing claims in these papers. So some really say there's overprediction if you would measure on the body. Some say there's underprediction. Some say there's not a significant difference between some positions. Some say there is a significant difference. But generally, most papers indicate that measurements at the chest more closely approximate eye level measurements than those at the wrist. And well, what we see in these papers, and also what we made hypothesis for, is that actually the results in each paper are really dependent on the context. So basically, where did they do the measurements? How did they do the measurements? Who were the participants? What were the participants doing? And where were the participants? So based on this, we formulated 3 contextual factors, which we thought would be relevant to investigate to see if those factors can basically explain these differences we see between the papers. And the first contextual factor we looked into is the illumination field. So, for example, if you would have a dosimeter here at the eyes and one on the chest, and then if you would measure on a fairly uniform illumination, then probably you're going to find quite similar measurements. On the other hand, if you would measure in an environment with very directional lighting, so for example, a light beam just on your face, then actually you're going to find quite the difference. Similarly, the posture of the participants, so basically the type of activity they're doing. If you have a posture in which the orientation between the head-worn device and the one on the body is quite a different orientation, then probably you're going to more quickly find differences between both positions than when they're actually orientated in the same direction. And related to this is also the body shape or the body morphology of the participants. So since dosimeters, especially new ones, are generally very small, if, for example, you wear them around your neck, then the device will typically follow the orientation of the outer contour of your body. So dependent on your body morphology, the orientation of the device and the placement will differ a bit. So we're also wondering if this could be a cause for differences between participants. So since these are all already relatively specific, what we actually did was what we set as a goal, that we would like to see if we can get an understanding of the impact of such contextual factors. So for example, if we know in certain illumination fields, for example, indoors, that there are very large differences between some body positions, or if we know that during certain activities, differences will be very large, then we can basically give some recommendations for informed dosimeter placement. So know under which conditions a certain body position may be appropriate to use and which conditions it may not be the case. So to investigate these factors, we did some experiments. And so the goal of these experiments was to investigate the impact of the context on the in situ performance of dosimeters. And since we really wanted to be able to basically see what does each factor result in if you just look at the final measurement, we developed a novel approach which consists of lighting simulations and 3D body scans. So we really could pinpoint for each contextual factor what the possible impact would be. So as a starting point for these experiments, we said, what if we only consider the posture of the participant, so basically the activity the participant is doing, and the body shape of the participant, and then not yet consider the illumination field. So only very theoretical approaches. And then ask ourselves the question, why would we find deviations between measurements at different positions on the body? So what we did, we basically defined 3 possible factors that we think could explain why there would be deviations. And the first one is translational dosimeter displacement. So basically, if you would measure the reference light exposure at the eye and somewhere on the body, then there will be an absolute difference in the location. Similarly, as I said, most dosimeters will follow the outer orientation of the body. If you place it somewhere, so for example on the chest, then if it's high up in the chest, then typically it will be orientated a bit upwards. So then there's also a difference in the rotational displacement of the dosimeter relative to the view direction of the eye. And lastly, if you would place a dosimeter just in front of the eye, then it's generally quite unshaded. Maybe it just barely has some shading of the tip of the nose. But if you would place it, for example, on the chest or a bit higher up, so it's underneath the chin, then your body can put some shade on the device, which can also impact the measurements. So we refer to this self-shading as body self-occlusion. And theoretically, if we would just minimize each of these factors, so find the point where they're all small as possible, well, then you just get to the eye, of course. But before that, maybe there are some positions on the body where all these effects are generally quite small. And well, to find these positions, of course, we first need to know how do these effects vary across the body. And then based on that, we can get some idea of the most optimal position to place the device. So for this, we need basically some body scans of different types of people. And here we decided to first basically focus on office workers, since especially for non-image strong effect studies, we see that indoors typically light levels during daytime are a bit more critical if there's enough daylighting available. And of course, office workers spend a lot of their time in these offices. So what we decided to do is just get a relatively small sample of participants. So we only had 12, so it's mainly an illustrative sample. And then we asked their participants to basically do different types of tasks you would see in an office, and then we took 3D body scans of them. So all scanning was done with this handheld device, and then the resulting 3D models look like this. So first we have people that were standing. Then we also had people that were typing on the keyboard and looking at the screen. And then we also 3D scanned people while they were writing with a pen. So basically they were doing this activity, but frozen for the 3D scan. So then you also see with the red arrow, the view direction indicated. So for the standing, it was in the distance. For the second one, it was towards the screen. And then for the third one, it was towards the desk because they were writing. So if we look at one of these models, they basically look like this. So you see the full body scanned, and also we included the table for the seated poster and of course the chair. And for each participant, for each poster, then we defined a virtual camera, basically so we could take an image of the participant with this camera. So what we can do then with that image, so if you remember these three effects, basically what you can do for each possible position on the body, you can calculate the magnitude of each effect. So we can calculate for each position on this 3D model, how far are we from the eye, what is the difference in rotation relative to the eye, and also at each position, how much of this, if I would place a dosimeter at the position on the body, how much of the dosimeter's view is actually shaded. So what I'm now going to show you is the same picture again, but now every position on this participant is shaded based on the magnitude of one of these three effects. So for the first one, the translational dosimeter displacement, so basically the distance from the eyes, you can see with changing color, the distance increases. So if it's dark blue, it's at least 0.8 meters from the eyes. So especially the hands, because they're a bit farther away in the keyboard, they are now dark blue. We see, or you can actually see for the eyes. So we took here for this one, the center point of the eyes. So if it's close to the eyes, it's in yellow. We did the same for the rotational displacement. So now here you can see any surface that has the same surface orientation as the view direction. And the view direction in this case is straight towards the camera. Then it's yellow. If it's more than 60 degrees off, then it's in dark blue. So for example, the top of the hands, you can really see there, well, there's quite a different orientation if you would have a wrist-worn device now than the view direction of the eyes. And lastly, we also did this for body self-occlusion. So basically, we, at every possible position on the body, we did a calculation. So if you would place a dosimeter there, then how much of the dosimeter view is shaded. So you see for areas with relatively little shading, so for example, the top of the head, it's about 0% in yellow. And then for areas with a lot of self-shading, so for example, under the arms or under the chin, it's at least 40% or more in dark blue. Also interesting here, you can actually see, so we as humans, we know our eyes are a bit shaded with field of view occlusion, and it's actually also visible in these images. So you see a bit of shading, self-shading around the eyes. So this is just one of the participants. Of course, we made these images for all our participants, so you can actually see a bit just by looking at them with all the different people, how do these effects typically relate over your body. And we also, so this was the poster when they were looking at the screen. We also have some pictures of when they were writing. So when they were writing, you still see that the translational dosimeter displacement is quite similar, of course, since distances don't change that much, but especially for the rotational dosimeter displacement, because now people were actually looking down a bit towards the desk, and they also angled the torso a bit more forward. So you actually see quite high rotational displacement values now, so typically more than 60 degrees. And also body self-occlusion increases a bit because if they bend a bit forward, then of course there's a bit more shade by the arms as well. So we also did this for the standing participants. And well, when they're standing, typically the torso is in line with the view direction of the head. So then actually most effects become relatively small. So just based on all these images, so I'm only showing 5 of them here. We had some more. We could ask ourselves what would then be the optimal position to wear this dosimeter. And if we go back to our example participant, then of course we could now look into these images and then try to see if there's a position that all effects are relatively small. So for example here. But of course, because we have 3 different effects, there will always be a bit of a trade-off. So then it's mainly about figuring out which one of these factors is the most important one we should control. So is it mainly about limiting the distance from the eye? Is it mainly about keeping the same orientation? Or is it mainly about minimizing the body self-occlusion, so the shading by the body? So, well, to figure out which one is the most important one to control, we actually need to now look into some illumination fields, since the impact of any of these factors will always be dependent on the illumination field under which you do the measurements. So what we then try to do is basically define some typical illumination fields you could find indoors, but make them generalized representations. So we want these illumination fields to be able basically to give us the needed information on how these effects interact, so which one has the largest impact. And these illumination fields basically should, in a generalized way, represent the illumination fields you can find indoors. So if you know the deviations under these fields, then you also know basically the range of possible deviations. So, well, we ended up deciding to just use 3 different scenarios. And the first one was one we refer to as diffuse top lighting. So basically in this scenario, we just have a room with the complete ceiling defined as a light source. And this light source is perfectly diffuse. So this is the lighting you can find if you're under a skylight, or for example, if you're under diffuse ceiling lighting. So if you would wear a dosimeter at the eyes, then your view would look like this. So you see the complete light source, and you also see at the bottom of the image just the tip of the nose visible, because the dosimeter was just positioned in front of the eyes in this case. Then we also defined a second scenario, referred to as directional top lighting. So this is using the same location for the light source, so again on the ceiling, but now the lighting has a strong directional component downwards. So in most offices, typically we see the lighting is designed to optimize the task lighting, so there's a lot of lighting on the desk, and if you look into the distance, you don't want to have glare from the light sources, so the lighting is quite downwards. So that's what we simulated in this scenario. And then we also added a scenario called diffuse side lighting. So basically, this is perfectly diffuse lighting coming from vertical plane. So this can be can be used to identify if you have lighting, for example, from a window or from a screen. So any lighting coming from a vertical plane, what can then be the measurement deviations? So these scenarios are just very generalized, but these are the different types of light source distributions you can find in an office. So they can give us the needed information on what range of deviations we can find. And so that's the eye level dosimeters. And then, of course, we're interested in what would then be measured on the body. And of course, the amount of places we can put the dosimeter on the body are endless. So what we decided to do is focus on 4 positions on the chest. So at the upper central, lower central, upper lateral, and lower lateral. And it's mainly because, on the one hand, of course, these are positions that we see quite often used in studies, but also just as we have at some different positions information on deviations and how the translational displacement, rotational displacement, and body self-occlusion interact, then we can also use that to get an impression over what will happen on the whole body. So at these 4 positions, we placed the dosimeter. Then we orientated that dosimeter following the outer surface of the body again. And then for each of these lighting scenarios and dosimeters, this is what typically the dosimeter view will look like. So in the upper central images, you see, since the dosimeter looks a bit upward, you still see the nose and a bit of the face. And for some other ones, you also see just at the side of the dosimeter view, some of the face. So this is just for one example participant. Of course, we did this for all the participants. So dependent on your body morphology, the orientation of the dosimeter will change a bit. And we also did this for the different postures. So what I'm now going to do is show the differences between dosimeter worn on the upper central chest relative to the dosimeter at the eyes. And I'm just going to show that for this case. So, well, here's an empty graph to start with. And on the y-axis, we have the mean relative difference to the eye. So basically what this means, if the dosimeter on the chest at this position would measure a higher irradiance value than the one at the eye, then there's a positive difference. If it would measure a lower irradiance value, then there's a negative difference. On the x-axis, we have our different postures. So the standing, the seated while looking at the screen, and the seated while writing. So, and now I'm just going to show the average results. So basically from all the participants, the mean deviations. So for the first lighting scenario, the diffuse stop lighting, we saw that for standing participants, there's a slight overprediction of the chest-worn dosimeter. For participants who are looking at the screen, it's actually quite similar. And then for participants who are writing, there's quite a bit of overprediction. So also what you see here now is that for each one, we have multiple measurements points. That's basically because we moved the subject through the room. So we put it at 7 different positions in the room to get also some impression of how the reflectances of the wall impact the results, because people are at different positions in the room, and the rooms were all quite generalized as well, but just to show a bit of the possible range. So for the second scenario, the direction on top lighting, we see there's a bit more overprediction for the standing and the screen facing participants, and it's a bit less for the writing participants. And then for the diffuse side lighting scenario, we see generally there's a bit of underprediction for the first 2 posters and a bit of overprediction again for the writing poster. So the first thing to note here already is, of course, so dependent on the posture, but also dependent on the type of lighting that's most prevalent in a certain space, you're going to find quite a different deviation between body worn and eye level measurements. So then, of course, it's quite interesting to figure out for each of these mean deviations, why is there this size of deviation? So remember the translational displacement, rotational displacement, and body self-occlusion. Which of these factors is mainly causing these mean relative differences? So if we would just look in the translational displacement, so basically what would happen if you only move the dosimeter lower, keep the same orientation, keep the same body self-occlusion, so basically none, then we would see that consistently the dosimeter would underpredict or about measure the same irradiances. And in our scenarios, that makes sense because, of course, the lighting is at the ceiling or further away in the room. So if you measure a bit lower, then typically you're going to measure lower light levels. Then for the second one, the rotational displacement. So if you would only consider that the dosimeter has a different orientation on the chest, but it's at the same position at the eye and there's no body self-occlusion again, then we would see that generally the dosimeter overpredicts light levels relative to the eyes. And lastly, if we would only look into body self-occlusion, then actually, so basically compare what happens if you have body self-occlusion, what happens if you don't have it, then we would see again that the chest-worn dosimeter typically underpredicts light levels at the eye, and that's of course because it's partly the field of view is shaded. So now for each of these mean measurements, so for example, the first one in black, if you would count the contributions of the translational displacement, rotational displacement, and body self-occlusion, then you would actually find the mean measurement value. So there's quite some information in this plot. So basically, what do we see happening here? Well, first of all, I think it's good to mention, so over all the different scenarios we considered, so all the different postures, all the illumination fields, then on average, we found a mean relative deviation between -26 to about 82% for these scenarios. So that's the possible range of values you can find under our simulated lighting environments. We also see that if there is more considerable overprediction, then typically that's due to the rotational dosimeter displacement being relatively large. And maybe you remember from the images I showed of the different postures, and when people were writing, so they were bent towards the desk a bit, then we saw on the chest, a lot of these positions had rotational dosimeter displacement of at least 60 degrees. So that's also what we see here in these results. So for the third posture, we see there, because the rotational dosimeter displacement is relatively large, the measurement error resulting from this factor will also be relatively large. And additionally, we also saw in these results quite some inter-individual variability. So for some participants, there was then quite some overprediction, while for some there was underprediction in the same scenario. So that was actually something we were quite curious about. So here we just had 14 participants, and of course they have different body shapes, but also we asked them to just position themselves doing this activity. So there's also a bit of difference in how they position their body. So we also decided to further look into inter-individual variability, and then especially due to body morphology. So for this, we leveraged a database of about 3,000 standing individuals. And on each of these people in this database, we also positioned a dosimeter just in front of their eyes and centered, and then also at these 4 positions on the chest. So, because of course that's a lot of work, made a script that automates it. So here you see for each participant, the dosimeter at the eyes and the 4 chest positions we considered. And of course, the dosimeter on the chest is orientated based on the body surface orientation. Then we simulated the irradiance measured by these devices in the 2 scenarios, the diffuse top lighting, diffuse side lighting. And then this was a plot of the results for the upper central chest. So actually, if you would look in the first column, so for females, and then under diffuse top lighting, you can actually see that there. So this box plot is just from all the 3,000 participants. So each participant is 1 data point. You actually see there's quite a bit big spread. So basically, if you would look at the interquartile range, so for the first 25%, first quartile of this population, we see that the mean relative difference to the eye is somewhere between about -10 to about 24%. Well, for another quartile of this population, this difference will be around between 40 to 70%. So basically, the only thing that's different between these people is their shape of their body. For the rest, they're in the same lighting environment. So it's quite an interesting consideration that there can be quite a difference in measurement just resulting from how the device is orientated on your body. If you're interested in this, it's actually already published. So I presented this last summer at the CIE midterm meeting. So I should, of course, also mention some considerations. So, of course, this was all simulation-based studies. So our results are basically scenario-dependent bounds. So in any real environment, the actual deviation will be based on the contributions of the different light sources. So basically, where is the lighting coming from, and what does this illumination field look like? So our illumination fields were relatively generalized. So there were some scenario dependent cases. So it can give an impression of the types of lighting you see in offices. So we know the deviation in these environments. So typically, we can say, okay, our cases give a certain range, but you should always consider, of course, real world illumination can be quite heterogeneous. So then there can be, of course, exceptionally large deviations than the ones we present here. I think it's also good to mention, always consider, of course, the required accuracy of your data. So what we're trying to do here is get the most accurate personal light exposure data, so basically the most relevant approximation of eye level light exposure. But if you're going to use the data, for example, for a metric during the daytime that's not that sensitive to fluctuations, then maybe it could be possible to just use a dosimeter at a certain position that's really not obtrusive, maybe not so accurate. and still get basically the needed information. So I would say always consider the intended use of your personal light exposure data. And of course, this study has some limitations, so we only considered 3 different static postures. So the results we presented won't be valid for all the different postures there are. And similarly, we use 3 generalized scenes. Well, of course, there are many more scenes. And also, we didn't consider spectral properties of lighting here, since we just used one channel related simulation. So it's mainly about the geometric component of the lighting and not so much about the spectral properties here. But of course, if you know the spectral properties of each light source, you can still determine which one is the most important on the resulting measurements. So to end with some takeaways and the outlook for the next steps. So first of all, what we've seen here is that the performance of a body worn dosimeter will always depend on where you place it on the body, the illumination conditions where you do the measurements, the posture of the participant, and also the body morphology of the participant will have an impact. So especially in all the papers, we sometimes seen that, for example, there's like a formula that they say, okay, you can use this formula to correct measurements taken at the chest to actually get more closer to eye level light exposure. So I would say don't, all the past studies are quite relevant to get an impression of the uncertainty, the possible uncertainty of your measurements, but generally it's not possible unless you have exactly the same conditions to use any absolute correction value. We've also seen that if you have a small shift in positioning on the body of for your dosimeters, for example on the chest, that can actually lead to quite substantial deviations between the translational displacement, rotational displacement, and body self-occlusion. We've also seen that there were actually quite some substantial deviations between our simulated body worn and eye level measurements, and that the main contributor to these deviations is the rotational dosimeter displacement. So what we would, based on this, what I would recommend to do, of course, first always consider the required data quality, and then if you want to get basically, for example, use chest worn measurements and get them as accurate as possible, so relative, of course, to an eye level dosimeter, then I think it's relevant to consider an individualized approach. So basically, for each individual, select a position where the rotational displacement is as small as possible. So if you know your participants, you know their typical occupation, so basically what tasks will they be doing most of the day. So for example, if they're seating, typing, and looking at the screen, then for that position, determine which chest position has the closest match with the view direction of the eye, and then position the device over there. In our results, it appears that it's acceptable if this position is a bit lower on the chest, since the translational displacement had a relatively limited impact. And lastly, we've seen body self-occlusion generally for the considered chest positions was not a concern, but of course, you need to avoid using positions with high body self-occlusion. So for example, just under the chin or underneath the arms. If that's not feasible, then of course, if you would like to use a standardized approach, so just use exactly the same measurement position for each participant, then in our results, we saw that the smallest range of possible deviations was present for the dosimeter centered on the chest at 0.35 meters below the eyes. But considering this, if you know your participants are going to be in certain postures that basically result in a mismatch between where they're looking and their torso, then it would make sense to consider using a head-mounted dosimeter, since if the rotational displacement is consistently large during a lot of the measurements, then the mismatch will also be relatively substantial. So then what's next? So basically what we're doing now is actually going back to the real world data. So in the Melidos project, there was a lot of light dosimetry data gathered at different geographical locations. So this data consists of measurement at multiple positions on the body, as well as a lot of contextual information. So basically the location, what were they doing, what were the activities. And then now we're trying to see, just based on real world data, which of course has a lot of factors that influence the data, but can we also explain based on that data the differences between light measurements at multiple positions on the body. And also, of course, we're interested in then we have a lot of data on these possible deviations. So can we also see for which personal light exposure metrics, if you know you're going to be using those, for which will these measurement differences become critical. So for now, thank you for your attention.